In this video, we'll focus on the free radical halogenation of alkanes. The overall transformation in free radical halogenation is the substitution of a hydrogen on carbon for a halogen, and that halogen comes from a molecule of molecular halogen. There are three mechanistic steps involved in free radical halogenation. There's the initiation step, in which radicals are formed by homolytic cleavage of a sigma bond. There's a propagation step, in which a radical reacts with another reactant to form a sigma bond and another radical. And then there's termination steps, where radicals combine to form a stable sigma bond. This is illustrated in the reaction shown here, the free radical chlorination of ethane. The initiation step would involve a molecule of chlorine dissociating upon application of heat or light, homolytic bond cleavage, and you generate two chlorine radicals. When a chlorine radical encounters a molecule of ethane, it can abstract a hydrogen radical, and that would leave a radical on carbon. This is a propagation step, because in this process one radical is reacting and you're generating another radical, so a propagation or generation step. This alkyl radical could then encounter a molecule of chlorine and abstract a chlorine atom, generating another chlorine radical, and this chlorine radical could then get involved in another reaction of ethane, and this cycle goes on and on and on until all of the hydrocarbon is consumed, and at the end the radicals that are present can combine in termination steps, and these are the three possible termination steps that would be involved in this chemical reaction. In the previous example, free radical halogenation of ethane, ethane has all equivalent hydrogens. What happens during free radical halogenation with a molecule that has non-equivalent hydrogens? For example, propane. Propane has both primary and secondary hydrogens. Since there are 3 times as many primary hydrogens as secondary hydrogens, you might expect the ratio of 1-chloropropane to 2-chloropropane upon halogenation to be 3 to 1. However, in practice, it's more like 1 to 1. Why is it that we're getting more reaction than expected at the secondary carbon than the primary carbon? That is, we have some selectivity preferentially at the secondary carbon. Well, the answer goes back to the stability of radicals. We said earlier that the more substituted radicals are the most stable radicals, which means that they're most easiest to form. So a tertiary radical is easier to form than a secondary radical. Secondary is easier to form than a primary radical, which means that the bond strengths for a tertiary and a secondary and a primary carbon would increase in this direction. So that means that the more substituted a carbon, the weaker its bond would be. It's easier to abstract H radical from a tertiary carbon to form a stable tertiary radical than it is to, say, take a hydrogen atom away from a primary carbon to form a primary radical. So that explains why is it that we have a bit more selective removal of a hydrogen atom from a secondary carbon here as opposed to a primary carbon here, because the secondary radical generated upon abstraction of that hydrogen radical would be more stable than the primary radical that's obtained by abstracting a hydrogen at a primary carbon. When we compare free radical chlorination versus bromination, we find that bromination is much more selective than chlorination for the more substituted carbon. So the question is, why is radical bromination more selective for secondary and tertiary carbons than is free radical chlorination? And the answer is because of the difference in energy of the rate determining steps between bromination and chlorination. Bromination, it turns out, is an endothermic process, and chlorination is an exothermic process. This is the reaction energy profile of an endothermic reaction. The transition state structure is closer in energy to the products than it is to the reactants. And the Hammond postulate states that the transition state structure would then resemble more the products than it would the reactants. For an exothermic reaction, this is the reaction energy profile. And in this case, the transition state structure is closer in energy to the reactants than it is to the products. In this case, Hammond postulate states that the transition state structure would then more resemble the reactants than it does the products. In free radical bromination, a bromine radical abstracts a hydrogen from the hydrocarbon to generate a carbon radical, an HBr. This process is endothermic, which means that the transition state structure, since it is closer in energy to the carbon radical than it is to the hydrocarbon, has a significant amount of radical character. So the bond is already almost broken, and we have a lot of radical character on this carbon in the transition state structure. Compare that to free radical chlorination, where a chlorine radical abstracts a hydrogen from a carbon, and you generate a carbon radical and HCl. That process, it turns out, is exothermic. Therefore, the transition state structure, since it's closer in energy to the reactants, and the reactants is a chlorine radical and a hydrocarbon, means that there's not a lot of radical character built up on that carbon in the transition state. So the bond is not very much broken, and there's not a lot of radical character for free radical chlorination in the formation of the radical. And so both of these steps, the formation of the radical, are the slow steps, and the free radical halogenation. This explains the greater selectivity for the more substituted carbon in bromination than in free radical chlorination. In the case of free radical chlorination, the transition states for the formation of the secondary radical and the primary radical only differ slightly in energy, so you have only a slightly faster formation of the secondary radical than the primary radical. That is, the activation energies leading to each radical are kind of similar. Therefore, the rates of formation of each of those radicals are also similar. In the case of bromination, where there's a lot of radical character in the transition state, there is much greater selectivity for abstraction of a hydrogen off of the secondary carbon than it is over the primary carbon. So in this case, the activation energies leading to each radical are sufficiently different. There's a lot of radical character in that transition state, and therefore the radical resulting from the lower energy transition state forms fastest. Here are some problems dealing with free radical halogenation that you can attempt. Solutions will be posted on Blackboard. We'll finish with a discussion of the stereochemical implications of free radical halogenation on achiral and chiral hydrocarbons. In this example here, we have butane. Butane is an achiral molecule. It has two types of hydrogens, primary and secondary. When you perform monochlorination on it, you end up with 1-chlorobutane and 2-chlorobutane. 1-chlorobutane is an achiral molecule, but when you substitute at the secondary carbon, you generate a new asymmetric center. and you end up with two possible enantiomers of 2-chlorobutane. They are formed as a racemic mixture. So why is it that you get a racemic mixture, a 50-50 mixture of 2-chlorobutane? The reason you get a racemic mixture is because in the first propagation step, when the chlorine radical abstracts a hydrogen off of the carbon, you end up with an achiral planar radical. Remember, this is sp2 hybridized, so it's planar. And in the second propagation step, this radical will react with a molecule of chlorine to generate 2-chlorobutane and another chlorine radical. Reaction can occur from the left-hand side face over here. That would generate the S enantiomer. Reaction from this side, the right side, would end up with the R enantiomer. Since this is planar and it's achiral, the activation energy for reaction from the left-hand side face or the right-hand side face would be exactly equal. Therefore, if the rate of reaction is equal from either face, you'll end up with an equal amount of both enantiomers being formed. What happens when you perform free radical halogenation on a chiral starting material? In this case here, it's a single enantiomer of 2-bromobutane, R2-bromobutane, and you can monochlorinate in 4 distinct positions. Let's start by just examining free radical chlorination at C1 and C4. The first propagation step, when you chlorinate at C1, generates this radical. This radical will then react with molecular chlorine in a second propagation step to generate this stereoisomer of the bromochloro product. When you have free radical halogenation occurring at C4, in the first propagation step, you would generate this radical intermediate, which goes on in a second step to generate this particular isomer of the bromochloro product. Notice that in each of these reactions, the stereocenter that's present, the carbon-containing bromine, was not involved at all in the reaction. So therefore, in the product, the stereointegrity at that asymmetric center is retained. Therefore, you only get these two isomers of product because you're not generating a new stereocenter when you substitute at C1 or C4. When you perform free radical monochlorination at C2 and C3 of R2-bromobutane, it's a different story. For example, look what happens when you perform chlorination at C2. Once you remove the hydrogen atom off of C2, this is the asymmetric center, you go from a chiral center, an asymmetric center, to something which is completely achiral. And as we saw before, when you have a planar achiral radical, remember this is sp2 hybridized, in the next propagation step, when this reacts with chlorine, it'll react at equal rates from the front face and the back face, leading to, in this case, a 50-50 mixture of enantiomeric bromochloro products. Even though when you perform chlorination at C3 of R2-bromobutane, you've not destroyed the asymmetric center, you are generating a new stereocenter. So there are still stereochemical implications of this reaction. Notice, when I remove a hydrogen atom off of C3, the configuration at C2 is retained. I generate a radical, and I have the potential of attack from the front face or the back face. It wouldn't be 50-50 because this asymmetric center over here is going to make the rates slightly different from attack from the front face or the back face. Nonetheless, I will have attack from the front face and the back face. From the front face, I would generate this new stereocenter. Attack from the back face, I would generate this new stereocenter. Since C2 stereochemistry has remained unchanged because no chemistry was going on here, but I am generating a new stereocenter at carbon number 3, I have generated not enantiomers, but I've generated diastereomers. With all that said, free radical halogenation of alkanes is really not a synthetically useful reaction. You will probably not be using it very much in solving synthetic problems. And why is that? Well, for example, when you do free radical chlorination, monochlorination on a hydrocarbon like this, you get a gross mixture of products. And when you perform a synthetic reaction, you want to get one major product. That's what makes a reaction valuable, if you have one major product in high yield. This gives a gross mixture because of the not very much selective nature of monochlorination. Sometimes it's possible to use it as a synthetically useful reaction. In this case here, this molecule has only one type of hydrogen in the molecule. So if you perform monochlorination, you only have one possible product. Bromination is more selective, and it can sometimes be used selectively to form alkyl bromides from hydrocarbons, but only in certain cases. Like for example, here we have all primary hydrogens and one tertiary hydrogen, so it's much more selective for tertiary hydrogens than it is for primary. So that's why you have one major product here